Before calculating derivatives or limits, you need to lock down the guaranteed points on your Chapter 1 exam. That means mastering the basic mechanics of functions. Let's start with where a function crosses the graph's boundaries. A zero is exactly where the line hits the horizontal x-axis. The y-intercept is where it crosses the vertical y-axis. To calculate the y-intercept algebraically, you set the input x to 0. For the function f of x equals negative 4x plus 2, plugging in 0 eliminates the x term, leaving an output of 2. Your y-intercept is the point 0, 2. Finding a 0 requires the opposite setup. You set the entire output, f of x, equal to 0. When we write 0 equals negative 4x plus 2 and solve for x, we isolate the variable to find a 0 at positive 1/2. Knowing exactly when to force the input to 0 versus the output to 0 is a simple check, but mixing them up is a frequent mechanical error on early tests. Pin down the difference now. Next, we have piecewise functions. These are multiple equations packaged together, but each one is locked behind a strict domain rule. Think of those domain conditions like a bouncer at a door. You cannot just plug an input into every equation you see. You have to check the number against the domain condition first to see which line it is allowed to enter. Try applying this logic yourself. Pause the video for a few seconds and evaluate f of negative 3 and f of 2. Let's check the first one. Our input is negative 3. Since negative 3 is less than 0, the top equation rejects it. It routes exclusively to the bottom equation. 4 times negative 3 plus 3 gives an output of negative 9. Now for the input of 2. Because 2 is greater than 0, the bouncer sends it directly to the top equation. Negative 2 plus 1 gives an output of negative 1. Treating these domain constraints as absolute gatekeepers keeps you from evaluating a single input against an incompatible equation. This image shows two distinct types of symmetry: a U-shaped curve mirroring across the y-axis and an S-shaped curve mirroring across the origin. Spotting this visually is straightforward, but on a calculus exam, a visual check won't get you full credit. Your professor will expect an algebraic proof to verify symmetry without relying on a graph. You have to prove the behavior of the function by intentionally testing negative inputs. Here are the two conditions you need to test. If plugging in a negative x yields the exact same original function, the function is even. If plugging in a negative x yields the exact opposite of the original function, it's odd. Let's test the function f of x equals x cubed minus 4x. The critical first step is to wrap that negative input in parentheses before applying any exponents. So we write negative x in parentheses cubed minus 4 times negative x. A negative value cubed stays negative, giving us negative x cubed.
Minus 4 times negative x becomes positive 4x. To compare this cleanly to our starting point, we factor out a negative 1. The result is negative 1 times the original x cubed minus 4x. Because the output is the exact opposite of what we started with, we've proven the function is odd. Mastering this precise manipulation of negative signs is mandatory. When graphing calculators are prohibited, algebra is your only proof. Here is a W-shaped polynomial curve. A vertical line test confirms each x value has only one y value, making it a valid function. The curve touches the x-axis at two zeros, negative 1 and positive 1. The perfectly mirrored sides confirm even y-axis symmetry. Here is your mechanical cheat sheet for function basics. To find zeros, set f of x equal to 0. For y-intercepts, evaluate f of 0. For piecewise functions, check the domain condition first. And for symmetry, plug in a negative x. Commit these setups to memory. Internalizing these mechanical rules guarantees you collect the foundational points on your early calculus exams.